collaborator, and most recently, a new colleague at the university, at Vanderbilt University, Jonathan Sprinkle. Jonathan Sprinkle is currently a professor of computer science here at Vanderbilt. He joined about a month ago as part of a major $100 million hiring initiative from our chancellor to bring in experts that can help build out our computer science program and expand our efforts in cyber physical systems. Jonathan has obviously played an important role in the CPS community since its founding. Prior to joining us at Vanderbilt, Jonathan was previously the Litton Industries John M. Leonis Distinguished Associate Professor and the interim director of the Transportation Research Institute at the University of Arizona. Before filling that role, he played an important role at the National Science Foundation, where he was program director in the Cyber Physical Systems and Smart and Connected Communities programs within NSF. And those are obviously two extremely important and high visibility programs that he was directing. Jonathan, his research interests have been in vehicle automation for some time, but I think what stands out is basically his willingness to deal with folks outside of his community, including folks like many of us on the call, to understand how automated vehicles might have many larger scale impacts. In addition to the research contributions he's had, he's also played a very important role in broadening participation through the CAT Vehicle REU program, which has been transformative in opening up opportunities for students to get hands-on experience with automated vehicles and autonomous vehicle technologies, for which obviously all of our fields are better off for. So without taking up too much more of the floor time, Jonathan, it's a pleasure to have you here, and we're looking forward to your talk on software and hardware challenges in vehicle sensing and control with commodity components. So floor is yours.
Thank you so much for the very kind introduction. I hope that my slides are visible, and in addition to that, that you can actually hear what I'm having to say. If something comes up and I start missing it, I think, Dan, you know how to contact me to let me know that time is up or whatever. It's really a pleasure to be here. And what I want to highlight, in addition to the fantastic folks that we see in the audience, I've heard several other speakers also comment on, you know, what a great array of collaborators and friends that we see online here.
Hey, Jonathan, I may let you know that you are doing a screen share that we can see all of ourselves back on your slides.
Oh, sweet. All right. Well, let me stop this one more time.
And it fit nicely with you telling us how pretty we all were, but I'm not sure you want us there for the rest of the talk. So,
well, we're going to try it one more time then. I don't know. That's the first time I've ever actually seen. What if I just share and share alike? And now we do this. So participants can now see my screen. If I show the video pane, do I get to see y'all again too? Do y'all see yourselves now?
Yes.
Still yes.
Yes,
okay, well, I'll hide that then, and then you won't have to see yourselves again. But now you just get the slides. Yeah, what a fun thing to realize all of a sudden that the new version of Zoom actually does this. So what I want to highlight then is maybe the large number of bolded names down at the bottom who are folks who contributed to data that show up in this talk, or that also contribute directly to some of the results that I'll show. I am the speaker here, but especially without Dr. Matt Bunting, Rahul Badani, and Safwan El-Madani, a lot of the software that you see that's showing up inside of this presentation would not able to have been written. And so for many of the things that I'm going to be able to show you here, a lot of these are based on their work, and I'm just kind of representing it from the perspective of the principal investigator. We've heard quite a bit recently about this issue of doing societal scale work. And one of the things that I've been passionate about recently is to understand that unless you have societal scale data and research test beds that can be deployed in societal scale situations, that simulation itself is not going to be enough. We still need simulation for a big piece of what we're going to be doing. But unless we actually have some way to deploy what we're going to show, we're going to run into these little things that don't seem like they're research, but they really impact what the research results might be. And as much as we might be able to correct things post hoc, we can't do it if we find out when we're in the field that something needs to be blatantly redesigned and there's no way to recover from it. And I think many of the great results that I've had with the collaborators here have resulted in understanding on, say, a Thursday night, what we were doing was wrong and we need to change it now so that we can use it tomorrow. And unless you have a great model-based process, unless you have an ability to substitute one component over another, unless you have an ability to rerun regression tests to see what your system would do if you were to make that change. You're going to be perhaps risking someone's life before you show out and make just a dramatic change that nobody else is going to be having an impact with. So if you accept these three kinds of things, which are a great outcome from the 20+ car experiment that I lost count of how many times we've seen the video of, I'll just put these three things up as sort of a beginning credo or tenet of things that's here that are challenging. The first is that capturing the data is laborious. The second is that you can only get real ground truth if you have many orthogonal types of sensors and you're able to correlate those so that you can understand exactly what the real thing happened on the ground. And the third is that you really almost always are validating your results with those data, but you're not necessarily using those as the inputs to your controller. And so if you can make some changes there, if you can shift so that 1 and 2 become easier to do, and that number 3 is something that you can really focus on a faster timescale, then that allows you to accelerate the role of data and discovery. And that's why I'm so excited to be a part of a team that's enabling the consistent and almost constant acquisition of data from a societal scale so that we can turn that around and have the various reinforcement learning or canonically derived controllers be impacted based on those data so that we're less surprised when we show up in the field. Again, these examples that we saw in the videos of previous work will not work at the kinds of scale that we've typically been operating, just because this CAT vehicle that showed up in both of these experiments only costs about $35,000 plus another $100,000, $120,000, $130,000 worth of sensors and time in order to get yourself that kind of system. So if you want to deploy, and I remember seeing this on Kathy's slides as well, you know, if you want to have a really high percentage of automated vehicles and have it work at a large scale, you just can't afford to buy those kinds of vehicles. And moreover, it's unrealistic to assume that people are going to actually spend that much more on those kinds of cars. But it's not unreasonable to think that folks will buy modern cars that have convenience features like the ones that you will find with Toyota, with the Toyota Safety System 2.0, so that they have many of those sensors that we have to bolt on with an Allen wrench, or that we have to buy a new bumper for the front of the vehicle so that we can attach it to the front and get telemetric data from. If we're able instead to depend on the kinds of sensors that are being deployed now at a commodity scale, then perhaps we'd be able to do an acquisition of those data and be able to use that either to train our controllers or to make real-time decisions. And that's where we're moving here. We're able to take advantage in this case of the Toyota Safety Sense 2.0, which is a standard feature that you see now in almost every car that you will buy off of Toyota lot, unless you're talking about like a giant truck. And for these kinds of systems, you get the benefit of short range radar for understanding obstacles nearby, or for understanding how about to run into the side of the car wash. You can get data that are giving you lead time information for the time gap that you have between you and the vehicle in front of you. You can get lane level information to tell you whether you're about to stray into an adjacent lane. And you can also get dynamic lane keeping features. All of these things are flying past us on this controller area network that exists inside of most modern cars today. It might be a slightly different kind of network depending on who manufactures your car and where it's manufactured. But at the end of the day, we have a bunch of wires that are connecting components that have a bunch of computers inside. And what we'd really like to do is just put a database on the end of that and use that database in order to make decisions as much as we can. And lest we forget about the commercialization opportunities that exist here, many, many companies are entering in this space. And the fact that the companies are entering this space permits us to take advantage of much of the engineering work that they may have done and perhaps improve mildly on that information. Unfortunately, a lot of the work that's done by those companies is good enough for some kinds of information, but not for CPS level research. As Dan mentioned, my background in CPS in the government meant that I kept reminding potential aspiring PIs that cyber physical systems deal with complexities of timescale that may be influencing you at millisecond levels, at second levels, at week levels, at hour levels. The fact that you have many of these competing timescales at which different components and different kinds of decision makers want to have information at different rates, that's a characteristic of these cyber physical systems. And if you just want to know, for example, the average speed that someone did, You can find that out later. You can log a bunch of data. You can miss a couple packets. And because of the dynamics of speed, it's probably not going to make a big difference. But if you want to differentiate speed to get acceleration and make real-time decisions on those data, you cannot afford to drop 5 or 6 packets, maybe 7 packets in between, if you're also hoping to understand whether or not someone has suddenly decided to decelerate. So we need to have some research quality data acquisition. We need to be able to add structure to the data that are there, and we need to be able to close the loop with some kinds of commodity computing hardware. Again, the reason that I'm stressing the commodity aspect of that is that if we're going to scale to, say, 100 cars, we cannot do it if we're going to expect to spend $5,000 and get a GPU for every vehicle. It's just not going to work. If we want to do 100 or maybe someday 1,000 or 10,000 deployments, we're going to be able to need to fit this eventually into something like an electronic control unit. But in the meantime, we're going to take advantage of tools such as ROS to allow us to do some real-time acquisition for research purposes. I think we heard a little bit from Rahul yesterday about challenges that exist for doing things with vehicles that need to rely upon simulation. And he also stressed a significant amount of his time in his talk about how to integrate things that might be coming from reinforcement learning and to simulate those reinforcement learning algorithms. One thing he did not have time to talk about is the amazing stream package that he and many of the collaborators have produced over the last few years, which has been looking at streams of data coming off of cars and decoding the CAN bus information so that you can get an idea of the dynamics of the vehicle. I unfortunately don't have time in the talk today to talk much more about that, but if you want to know more about Stream, reach out to Rahul. What I will talk a little bit about today is the architecture of libpanda and a companion software package called CAN2ROS that works from within libpanda. And as I mentioned before, this is led primarily by Dr. Matt Bunting, who's done some amazing work in order to make that happen. So what's the dream scenario for the kinds of data acquisition and control that we're doing? Well, part one, we'd love to be able to install some commodity hardware that somebody else has already designed and hardened for heat and other kinds of challenges, designed all the cabling for and built a bunch of APIs for. We want to plug that into an existing vehicle using the existing CAN bus hardware. So you can see here I'm unplugging in the upper left-hand corner the CAN cable that goes into the controller for adaptive cruise control. Once we plug that into, in this case, it's the old Panda Giraffe, but the idea is the same. We plug that into here, and then we plug the libpanda, or sorry, we plug the Panda itself into the car. And now we've got essentially a filter on the data that are flying through the car. So you can talk to Maya and Gracie about how long it takes to do this kinds of setup. Typically you're talking about on the order of 30 minutes to an hour, depending on how tight you want to hide the cables behind all the pylons, et cetera, to make sure that in the unexpected loss of cabin pressure that might come with a side impact or a front impact to the vehicle, that you don't have cables flying at you and everything can stay safe. Once you've done that, you plug in some of the cables into a USB on your Raspberry Pi or to some other computer. And after you've got that plugged in, you're now able to start up the libpanda software. libpanda itself will, if installed on a Raspberry Pi, automatically name that computer to match the vehicle VIN. So if you were to look closely at this video in the bottom left-hand corner, you'll see here as we're beginning to look at the web interface that's pushed out of the Pi's infrastructure, that we'll see the name of the VIN there, which is the name of the vehicle that it's plugged into. And we can also see that it's recording and has a great GPS fix. And finally, now that you've done all this, again, we're talking about an hour to 90 minutes total of getting all those things done. Your vehicle is ready to operate, either in data gathering or in control mode if you're able to synchronize it. And with that comes all the complexities that you'll see later when it comes to looking at the dynamics of traffic and being able to operate safely from within traffic. So that research quality data acquisition really comes from the libpanda side of integrating with with rad hardened kind of hardware that you can buy that will plug into your car. The idea, of course, is that we plug it in once it's installed. If you start on the car, your Raspberry Pi boots because it's also plugged into the onboard power supplies that are available for everything else that might be in your car. Because there's a GPS that's baked into the libpanda, to the Panda devices, you can use the information flying through on the GPS to actually set the time of the Raspberry Pi to match the current time of GPS time. Once that time is set, you immediately start recording on the vehicle. And when the power is disconnected, if your Wi-Fi is connected and you've got the battery backups installed, then you go ahead and upload your data to Cyverse. And once the data are synced, then the Raspberry Pi turns itself off. And so with this, you have kind of a brain off situation where you can install the information in your vehicle, record data everywhere that you go. And some of our privacy preserving algorithms inside of Cyverse strip off the beginning and endings of your drives so that you end up with only sharing information about when you're on public roadways and you're not on your way, or you're not stopping at an errand or having lunch or something like that, and giving away some private information that you don't care about. As I mentioned before, capturing all these data needs to have a little bit more of a real-time response. So that real-time response allows you to understand, in the worst case, that things are not behaving well. So libpanda itself is a C++ based infrastructure that allows you to do Panda data recording without a huge processor jump that you see with the native Python packages that they produce. Instead, thanks to Matt's work and also some help from Matt Nice and other folks looking at how to decrease the CPU utilization, we're able to look at the time arrival of packets and understand that the CPU usage is not reducing the amount of packets that fly through, and that we're actually getting, when you do time difference of all the messages, they're basically on the order of the jitter that you get with any operating system, or maybe even the jitter that's inherent in what's seen in the CAN bus. Since there, you may want to send a packet and someone else is already sending, so you have to wait just a few seconds, milliseconds before you send again. Once you get the data to come through there, you're also then able to, I don't know if this video will play or not, relay this over on top of dashcam data. So I'm going to skip a little bit far into this so that you can see kind of what I'm talking about. If you were to post-process these data and look at them, you would be able to extract and decode some information to see, for example, here what's leading in front of this car. You've got this little yellow square here. And you can see over on the right-hand side, this corresponds directly to following this vehicle. As we continue on, you'll start to see other things blip up on the side. So you can see now there's a Jersey barrier that came in there. As we near the exit over here on the right, we may have an opportunity where a car passes us on the left, and you can see that little yellow square is popping up again there to tell you that we're getting a radar fix from something that's in the lane adjacent to us. With this kind of radar information, you can make decisions in real time. And you may also be able to look closely and carefully about what you might want to do if you were to have a computer in the loop instead of a human in the loop. I think Dan articulated really well yesterday when it came to a human in the loop that we can use some of these CAN messages in order to make things make sense for a human, but we want to make sure that they'll make sense for a computer who might be making decisions too. But sort of suffice it to say that even if you have two of these vehicles with information on it, then you can start to see driving behavior as you extrapolate between the two vehicles, as you understand relative speeds, average speeds, relative following distances, and following time headways. Every driver has their own behaviors. And even in really short experiments where you're looking at this, you can start to get really insightful information about how behavior at large may be something of interest. Okay, that's great. We've been gathering a lot of data, but we also need to close the loop. And so I want to take you just a few slides through that architecture and then leave some time for questions at the end. I've been for a long time kind of glossing over, like, what does it mean to be interacting with the CAN bus and where do all of these things fit in? So I'm going to take just a few minutes here to really walk through what this looks like and what the architectures are like in case you've never really had a chance to think about this. So that Panda that you saw me plugging in into the top behind the rearview mirror, we have a new, more modern version of that called the Panda Black, which has a different kind of interface, but the idea is the same. That there's a CAN bus plug that plugs into something in the Panda Black's local universe. And that bus is a huge array of messages that are all arriving at different times. So those messages then, when we're plugged into the Panda Black through USB 2.0, allow the Raspberry Pi and any components that we have running on the Raspberry Pi to interpret those messages as we want. Sometimes we can send back messages to the Panda Black, and then the Panda will relay those also onto the CAN bus, which then talks to the adaptive cruise control, electronic control units on the vehicle. So really, we've just kind of unplugged one thing and plugged this one in, and that gives us the new kinds of behaviors that we're looking for. And where do these fit in the vehicle? Well, the Panda Black is kind of up in the rearview mirror area. The Raspberry Pi can go anywhere, but we've been typically setting it underneath the passenger side because that gives good access to other things. So if you're only recording things in libpanda, You've got this giant pipe of information that comes in. The Panda Black is just passing on everything that comes into it, but it's allowing you to sample what's coming through on that thread. And so libpanda subscribes to the data that are flying through on the USB from the CAN bus, as well as data that are coming from the GPS module that's on board. And then it saves those in two different files. One of them is the CAN data file, which is a fairly large database that is named for the current GPS time at which you started recording data, and then a companion GPS data set as well. So the CAN data and the GPS data are both timestamped with the current system time, but GPS data includes an additional GPS time in the final column that tells you at this particular time when we logged this is what time GPS thought it was. And it's an exercise still to look at how much do those times drift over time. How often do we get a timestamp that doesn't make sense, et cetera, et cetera, et cetera. So in recording mode only, this allows you to really have a passive infrastructure that's relying on the Panda Black to fly through those messages as you go. Once you start wanting to also control, things get a little bit more complicated, because now libpanda manages an additional interface through the APIs that come from Comma AI to allow you to pass through some messages automatically. So you can see that here where you've got the big bus in between, where the bus moves from one side to the other, all of these messages. And then some of these messages get pulled out and sent to libpanda. And libpanda may choose to send its own messages through the same portal. So this is the idea where you might be saying something like, I see that there's a request to accelerate that came from within the car. I'm going to substitute my own acceleration message here. And by substituting my own acceleration message, it's going to allow me to control the vehicle. What it does not do is influence whether or not you're recording data from the CAN bus or from GPS. So both of these things allow you to be able to still maintain the same kind of recording that you were doing before, but now be able to inject your own messages and see how the vehicle behaves. There's another package called CAN-to-ROS that was written by Safwan El-Madani and has, again, many collaborators on it. And with CAN-to-ROS, we're taking a subset of those messages that fly through libpanda, and we're extracting some of those messages and converting them into ROS. So the current setup that we have over here is shown on the right for these topics, that we're able to get information from the current acceleration of the car, whether or not control is currently allowed, whether the GPS is receiving information, whether the mini car is in front of us. The mini car is this little thing on your dash that tells you that you're behind another car. It also tells you whether you're commanding an acceleration and whether that commanded acceleration is going to be relayed on or not, is dependent on whether it's deemed to be safe by some other component called the follower stopper that you'll see in a few moments. So you can also see over on the right that the number of these messages differs between each component. And the reason that you have a different kind of response for every component is that you don't have a consistent determination of this distributed machine that operates in lockstep. You have an asynchronous behavior over which some components run at, say, 50 hertz or 20 hertz, and others run asynchronously. So you have no idea when you're going to get a new request from them. So with that capability to send messages through ROS, now we can spend a few moments just briefly exploring how to send those commands to impact the vehicle with respect to its own timing and dynamics. And much of this was done, again, out in the wilds of Arizona, where you have these great empty roadways where you don't see anything except your own vehicle. And that made it really safe for us to do this. Here's an example of one of those drives where we spent a lot of time speeding up and slowing down, speeding up and slowing down, speeding up and slowing down. As you begin to send these control input commands, as you may remember from your system ID background, what you'd love to do is send a step input and then measure the response to that step input. So after you send it for one step and then another set of steps and then another set of steps, you can start to build an array of responses and then do some approximation and system identification out of this for an array of inputs. So in this case, with inputs of so many meters per second squared, we're able to build the response of how we may see the system actually behaving. You can see that it's not perfect, that every single response doesn't seem to match every time. But part of the limitations that you may or may not experience here also has to do with whether or not there are physical dynamics that prevent you from responding at the rate you'd like to respond. One thing I would highlight on that is this input at 1.5 meters per second squared. At some point after 10 seconds of that, you can see that we no longer receive 1.5 meters per second squared if that's our constant input. And the reason for that is that as you speed up over certain speeds, The vehicle itself just can't deliver those kinds of accelerations based on the transmission and the engine size. And so as you're speeding up and slowing down, it's important to be able to understand that a request for a particular acceleration may not actually happen. So how does this impact our live use? Well, we've seen examples of these intelligent driver models. I want to posit here this unintelligent driver model. You can see this other vehicle operator here who just cruised right in front of us and zipped right around. These are the kinds of things that we've not been exploring a lot when it comes to our simulators, and that's why it's important to have live data that we see. Again, they come right through us. We're following the vehicle ahead at a place that we seem to be safe. That person pulled right in front of us and is just zipping around. So this will absolutely wreak havoc with your safety controller, as most folks know, unless you're prepared for it. The second thing is that we want drivers to only use their existing ACC buttons. So that requires us to have some internal logic that allows us to relay information about, say, the time headway, and then respond with particular accelerations, or say that we're going to decline to send those accelerations onto the vehicle if it doesn't make sense. Our typical inputs look like we have these energy reducing velocity controllers, such as those discussed by Eugene. It goes into a safety controller, which relays a velocity command to an internal controller that then finally relays an acceleration to the vehicle. So we can initiate our control, for example, when that velocity to acceleration command, if we look at it, that is desired acceleration. If the control operator has turned on the ACC, if they've established an ACC set point, and if the desired acceleration is either continue at this speed or speed up, then we can allow control to be enabled. It's unsafe for us to allow control to be enabled if, for example, turning it on right now would result in immediate braking. And so likewise, we automatically disengage control if the operator turns off the ACC or due to a cut-in. And libpanda over here on the right handles all of that by just cutting and then repasting together the messages through the magic of mad bunting. I want to give a few minutes for discussion in case there is any. And so I'll just conclude here by saying that although system ID and these kinds of things really make sense in order to establish your nominal behavior, you really do have to consider some of the non-traditional uses and think about the rapid response of your system with respect to the safety of not colliding in front of you, as well as understanding that you don't want someone to collide with you. And so a lot of the models that you may build there will really rely upon your discretion when it comes to deciding whether or not to enable control. I'll also finalize by saying, without all the many team members that you've seen referenced earlier, as well as some additional ones on the page here that are the overall PIs of the Circle project, none of this work would be possible. And so it's been my great pleasure to work in this area, and I look forward to any questions that you may have.
Thanks, Jonathan. I think we have time for one question now, and then maybe encourage folks to follow up with you offline as well. I'll open the floor for the first question. And then I will take that first question if no one else wants to jump in here. Final call. Sure, Jonathan. So I'm wondering, I mean, you've worked on a completely, customized automated vehicle platform, your CAT vehicle that does all kinds of things and doesn't do all kinds of other things. And then you've been working with these commercial vehicles that have their own sort of pros and cons. Where do you see sort of these, RAV4 type platforms in terms of like the research space that they can enable compared to the, customized platforms? Obviously, there's a certain set of things that you can't do with a RAV4 that you might otherwise want to, complete customized thing. Can you just give us a little bit of the landscape in terms of how you're thinking about the, RAV4 style platforms compared to the CAT vehicle?
Absolutely. One of the things that really excites me about working with the commodity vehicles as much as I can is that it streamlines the actuality that the work that I have might be able to be placed into production at some point in the future. I think if I were able to get results and all it did was require a complete redesign of the transmission or the addition of sensors that might cost $10,000, that's really going to limit when those kinds of impacts may come. And so I'm excited to be able to get more into using some of the commodity vehicles, even though there's a little bit of a price to pay in terms of determining how to get the data off in a way that doesn't compromise the intellectual property of whoever made that vehicle. At the end of the day, I'm not interested in competing with them as a vehicle manufacturer. I'm interested in making vehicles safer And that's what's enabled such a great collaboration with Toyota on this project, as well as with other OEMs, because they understand that if our goal is energy reduction and traffic smoothing, that using their existing vehicles can be a better pathway to make that happen.
Well, I think that's a great note to end on. Please join me in thanking Jonathan for a great talk here.